Hello everyone. In today's video, we're going to continue on 3.5, basis and coordinates. We're going to actually talk about theorems in today's video. This theorem is very confusing at some points, so I'm trying to make it clear on how these theorems work for you. And we most likely spend a lot more time in class going over maybe examples or or questions and answer how this theorem works. So the theorem is theorem 3.5.4, so you can actually make sure you go back to the textbook and refer to it and just read up on the textbook also, just to try to get more understanding and try to solve different things out. So the reason why this is confusing is because it's dealing with basically a function between two vector bases with two vector spaces with two different bases on each of the vector space, and how to correspond the two bases with the coordinate vector with the function that we're going to define, with the linear function that we're going to define. So there's a lot of pieces for this theorem to fit together. So therefore, it's very easy for students to lose track and get confused. So let's give it a try. Let's stay with the theorem today. So let's start with the following. Let's say we go define vector v1, v2, to vn. Be a basis for a vector space V. Notice that this vector space V has n vectors as its basis, so therefore implying that the dimension of V maybe I'll do this. The dimension of V is n. Now similarly, I'm going to define another vector space. I'm going to use W1, W2, to Wm to indicate that this vector space could have the same dimension but could be different dimension, be a basis for another vector space. And yes, you guessed it, this one I'm going to call W. And so in this case, the dimension for W is m. So here's the essence of this theorem, is what happens if I define a linear function f that go from V to W. Let f be a linear function f map from V to W, okay, such that this is true. Such that f of vector x equal to vector y, where vector x is in V and vector y is in W. So therefore, in this case, we're basically defining vector x to be an object in V, and then y is an object in W, and the function f kind of have this linear correspondence between them. Now, what does this theorem try to do then? Well, if you recall what we learned in 3.1, linear functions, we learned that every linear function going from Rn to Rm will have a matrix form. However, we also learned in 3.3 that if you have a linear function from one vector space to another vector space, if those two vector spaces are not Rn or Rm for that matter, but are different things like polynomials, like functions, then it might not be possible to define the function in matrix form until now. See, in this theorem, what we go try to do is the following. If we look at the vector x and y in vector space V and W, if they are, let's say, functions, then really no way to define this linear function f with continuous function space as a matrix form. But if we have a basis for the vector space, then therefore it means, like what we've been talking about for the past couple sections in chapter 3 already, if we have a basis for the vector space, I can actually define a vector in that vector space by using a coordinate vector in Rn. And therefore allow me to actually redefine a function that works between vector spaces that are not Rn into a kind of corresponding function that work with the coordinate vector of vectors in those vector spaces. So me in this case, I cannot directly form a function f in matrix form that can take me from x to y. But I may be able to form a function f in matrix form that take the coordinate vector of x into a coordinate vector of y. And if I can do that, notice that if I take a coordinate vector of x, that would actually be a vector in Rn. And then become a coordinate vector for y in W would technically become a coordinate vector in Rm. So I'm essentially trying to define function f on the coordinate vectors. And because of the way coordinate vector work, a list of scalars, coordinate vector are basically vectors in Rn. And now I can actually form a matrix form for that. So that's what we try to work toward. And which is one of the reasons why this theorem is quite confusing to work because of that. Now, we're not done with the theorem, so I'll show you. So here, let's say we do the following. Let's say vector x can be written as x1 vector v1 plus x2 vector v2 plus dot 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 plus xn vector vn. So therefore, giving me a coordinate vector, which is x1, x2, dot, dot, dot to xn. And similarly, I'm going to define vector y to be y1, w1, plus y2, w2, plus dot, 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 plus ym, wm. And so that becomes the coordinate vector, y1, y2, dot, dot, dot to ym. So now this is essentially what the theorem states. The theorem states the following. Okay? The theorem states that these two coordinate vectors actually has a correlation between them. Okay? And this is what the correlation, the coordinate vectors are related by the following matrix. So essentially, we can now define a matrix that actually relate the input and output. So therefore, we can actually define not the function f. Function f is defined for vector space v to w. We're going to now define a new function that kind of do the same thing as function f. But instead, this function work from Rn to Rm. They work for the coordinate vector. So it's defined by the following matrix. Actually, you know what? I'm probably going specific. It's defined by the following M by N matrix. So what is this M by N matrix? I'm going to call this function capital F of x1, x2, dot, dot, dot to xn. And that would equal to A11, A12, so a typical matrix. And I'll tell you what those numbers going to be. But just simply show you that we have a M by N matrix. Multiplied by x1, x2, dot, dot, dot to xn. And we'll give out y1, y2, dot, dot, dot to ym. So as I said, in this case, this function f actually now map from Rn to Rm. And this function f is linear because it's in matrix form and correspond the two coefficient matrix, the two coordinate vectors. Now the question comes down to then how do we actually define this matrix then? Well, this matrix is defined this way. In this matrix, where each jth column is given by f of vector v sub j equal to a1j w1 plus a2j w2 plus dot 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 plus amj wm. So now it's probably hard to understand what this means. What does it mean is the following. It means that when you want to form the matrix, each column is what happened when you put the corresponding vector in the basis of the domain into the function f. And its coordinate vector become the columns. Okay, so therefore in this case, maybe I can write it out in Word to help you kind of see. Okay, that means each column of this matrix is formed by the coordinate vectors in the basis of V in terms of the basis of W. Meaning you take each vector in the basis of V and form a coordinate vector in terms of the base of W. Now, if you think about it, some of you might actually recognize that you see something like this before. And yes, you have. As a matter of fact, you see that in here. You actually been tested on Theorem 3.1.3, where in this scenario right here, you're being asked to form a matrix that go into Rn to Rm, and the matrix that you're going to form is formed by f of E1, E2 to En, which is exactly what this theorem in 3.5.4 asks you to do, because each of these columns is what happened to f of V1, f of V2, f of V3, f of V4. The only difference is in this theorem 3.1.3, the output just become the column, because in this scenario right here, 3.1.3, we are assuming standard basis for both Rn and Rm. So therefore, whatever you put into E1 into F, whatever you get is in the standard basis already. So in other words, this theorem 3.5.4 is a more generalization of the theorem 3.1.3. Now, as I say, the theorem can be quite confusing to try to decipher. So best way to do that is through an example. So show you a very simple example to illustrate the concept, and also point out some of the things that will help you figure out how to sort out everything and form the matrix in the correct way. Imagine the following. Let's say we have a function f that do this. I'm going to let v and w both be in the same space just to make it easier. Okay? And we're going to go ahead and let the basis be just E1 and E2. So essentially, what we're doing is essentially the same thing as theorem 3.1.3. And of course, I'll show you what will happen if we use different bases. Oops. So let's say we know this. Let's say given f of d1 is 1, 1, and f of d2 is 2, 3. So now some of you probably already know, so according to 3.1.3, the matrix will be 1, 2, 1, 3. Just put these two columns together. But I want to show you how the theorem works in 3.5.4. Because once again, I'm not showing you this example because it's easy, but rather because it leads into, you can see how the theorem works, so that now you can, when you're dealing with problems with different bases, you can still take a step back and use the same exact method. So then based on theorem 3.5.4, this is what we know. F of vector E1 is equal to 1, 1, which is basically equal to 1 times E1 plus 1 times E2. Now, show you something important that will help you sort this out. This number right here is the number for A11. This number here is for A21. Now, how does that work? How does the subscript work? Show you. The subscript right here, that go here and here. The subscript right here go right in the front. That's how you sort out what entry the coefficient is in the matrix. So now let's do f of d2. So that will be 2, 3. So notice, because it's standard basis, just means 2 times e1 plus 3 times e2. So now the question is, based on what you just see, which place do you put these two numbers? Okay, so they are A. Okay, remember the number of the vector in the domain dictate the second number in our coefficient, and while the first number is basically just from the linear combination. This is 1, this is 2. So now I'm ready to write out my function f of vector x. Okay. In this case, technically speaking, is the same as capital F. And it would be formed by A11, which is 1, A21, which is 1, A12 is 2, A22 is 3, of x, y. And that gives you the vector y. So this was not terrible exciting. So how about we do one with different bases? So this one is, once again, very straightforward. Okay, what if we want to do, let's say, same vector space, R2, but using different bases to show you how this works. And then we'll go try to do one with, maybe with a different vector space, not Rn, to show you how this theorem work out with that. But let's do one with in R2, in Rn again. So let's say in this time I'm going to let the bases be vector b1, b2. And b1, b2 are 1, 1 and 1, 2. So clearly these two vectors are not multiple. So therefore we'll form a basis for v and w, basically for R2. Let's say we define a function f that go from v to w, and such that we know this. We know f of b1 is equal to 2, 3, and f of b2 is equal to 0, -1. So Now the question going to ask you to do this: apply theorems 3.5.4 to find F in matrix form. Basically meaning that we go kind of rewrite F. Instead of go from V to W, it take F that would take the coordinate vector of V into the coordinate vector of W. Okay? Well, actually, maybe I do this. Maybe I call that capital F because that's what I called it. Okay? So, how we go about doing this? So, give you a few minutes to take a minute to think before I show you what to do. Okay, so you can pause the video, and I'm going to continue in just 1 second. All right, so the first thing you probably realize is the following. This capital F of vector x is not equal to 2, 3, 0, negative 1 of vector x. Okay? Why not? Isn't that what is set right here? The problem is because the output 2, 3, and 0, negative 1 are in terms of the standard base, or is a position vector, but not the coordinate vector that relative to the basis that we are in. That's the problem. Okay, so what I need to do is to rewrite that. And then, yes, I know some of you are probably thinking, wait, but then we do want to give an answer that would be more universal. I don't want to get the coordinate vector. I want to get the position vector. In this case, think of like V and W are both in R2, which define position vector. And you're correct. The idea here is that once I be able to rewrite function lowercase f into capital F that can allow me to deal with the coordinate vector, that I can then use the coordinate vector with the basis to form the answer that we're looking for, the correct position vector. So, show you how that is done. Don't worry, this whole thing will be demonstrated to you. So, the way to properly form the matrix is to realize that the output that we given, f of vector b sub 1 equal to 2, 3, is basically essentially mean is 2 times vector e1 plus 3 times vector e2. The problem is this is a linear combination in E1 and E2, not B1 and B2, which is what we need. Because if you read the theorem 5.3.5.4, okay, in order to form this coefficient, the column, I need to rewrite the input of a vector in the domain basis as an output, as a linear combination of the vector in the of the base in the range. So we don't have that. Okay, I have to plug in B1 and I have to write it out as a linear combination of B1 and B2. So therefore, we can definitely go for looking for that, so which is not too hard to do. So in this case, I can think of the output is 2, 3. Oops. 2, 3. And that will have to equal to some number times the vector. Well, actually, maybe I'll write this way first to help us out. Some number times B1 plus some number times B2. Now, here's the important part that I want you to do. How do I enable these two numbers? Well, use the same method that we did here before. Notice that the subscript of the basis that we used, or the basis that we use to form the linear combination, is the first subscript underneath. So I'm going to go and call these two A1 and A2. But we also need a second subscript. The second subscript inherit from the input of the function, which is vector B1. So therefore, I'm going to say this is A11 and A21. Now what I'm going to ask you to do is go ahead and try to find A11 and A21. should not be too difficult to do if you simply think about it. A11, B1 is this, so 2, 3 is equal to A11 times B1, which is 1, 1, and B2, which is 1, 2. And it shouldn't be too hard to figure out that A11 is 1 and A21 is 1. Therefore, indicating the following. 2, 3 is the same as 1 times 1, 1 plus 1 times 1, 2. Therefore, forming the coordinate vector 1, 1. Or actually, better yet, I'm going to go write it vertically because they're going to form columns. Now I'm actually going to do the same thing with the second one, which I hope is not too hard for you to figure that one out. This would just equal to, but once again, I want you to write the subscript correctly. So this would be B1 plus B2. So therefore, this is A1 and A2 again. But this is f of B2. So this subscript 2 indicates the second subscript is 2. So therefore, it shouldn't be too hard for you to figure out that A12 is 1 and A22 is negative 1. So 1, 1 minus 1, 2 is 0, negative 1. And so therefore, what does that tell me is that the vector 0, 1, which is the output of f of B2, or 0, negative 1, I'm sorry, is equal to 1 times 1, 1 plus negative 1 times 1, 2. Therefore, form the coordinate vector 1, negative 1. And so now I have the correct function. The function f of vector x actually turned into this capital function f of the coordinate vector of x, and that's equal to 1, 1, 1, negative 1 times the coordinate vector x. Now, important to realize is the following. This function, capital F, does not relate the position vector. It relates the coordinate vectors. Now, how is that different? Okay, imagine the following. Show you how this is done. Okay, imagine the following. Let's say given vector v, which is negative 1, negative 4. What I'm going to ask you to do is try to find f of negative 1, negative 4. And so we're going to do that. We're going to try to do that to show what happened. But important to understand is that in here, when I list f of negative 1, negative 4, I'm imagining this is our position vector. And when we try to state the answer, I'm also looking for a position vector that is not relative to the basis that we use. Okay? So, how does it work? The problem, common mistakes to be made. Shouldn't I just put that 1, negative 1, negative 4 into vector x and multiply by this matrix and get an answer? No. Why not? Because this capital F function only deals with coordinate vector relative to a basis. This is a position vector. That means it's not the coordinate vector for the same position vector because in this case we're using a different basis. So let's start with the following. Imagine this. We have a basis which is which is B1, B2, which is 1, 1, 1, 2. So first what we need to do is find the coordinate vector of vector v. So how do you do that? Well, vector v would equal to negative 1, negative 4, which would equal to some number. In this case, okay, I didn't use letter V, so I'm going to go and say, in this case, it's going to be V1 times 1, 1 plus V2 times 1, 2. So now I'm going to ask you to do is go and tell me, find out what V1 and V2 is equal to. It shouldn't take you too hard to figure it out. All right, I'll give you a moment to do that, and you can pause the video to try to find that. And if you didn't get the right answer, you really need to double check your work. I mean, solving for these two numbers should not be the difficult part or part that you make mistake in differential equations. Okay, if you make mistake in 7th grade when you first learn it, yes, but in here you really shouldn't make the mistake. So if I'm not mistaken, the answer would be 2 and negative 3. So now I'm ready to do my problem. So if I take the function f and I plug in the vector negative 1, negative 4, that is the equivalent to taking the capital function f, which would deal with only the coordinate vector, and plug in negative 2, negative 3, because negative 2, negative 3 is the coordinate vector of negative 1, negative 4, with the basis of b1, b2. And so now I have the matrix that can relate the coordinate vector. So I'm going to do that. And that would give us this vector. Now, what is this vector right here? This is the coordinate vector of the output. So not the answer that we're looking for. So now how do I write out the answer? Well, that would mean that this is equal to negative 1 times b1 plus 5 times b2. So now I can simply just do my math, and that would come out to be 4, 9. So essentially, that's how the cap function f work. Is that it changed the function lowercase f into a function that deal with the coordinate vectors and allow us to actually find the output coordinate vector, then allow me to represent it into the proper space. Now, unfortunately, my video is already 32 minutes, so we'll go do the next example tomorrow video, and hopefully it'll make you understand why we do this. So the next video will be on a vector space that's not the R2 space, but I will try to mirror it to this exact problem so that you see how that worked out. All right, I talk to you later. Okay, bye-bye.